Hi, this is Kevin. Welcome to my Beyond the Textbook lecture that accompanies the work that we do with Chapter 6 of the Zelle 3rd edition Python programming book. Um, while we're working in this lecture, I'm going to show you some code. And in your weekly schedule, uh, you should have a place where you're able to download the code, and it should be called Demonstrations to Supplement Zelle 3E Chapter 6. All right, so that's the code I'm going to be showing and running and all that kind of stuff. So Chapter 6 was about Python functions, and I think it's a good chapter overall. The things that were covered well, which is why we're using the book. But there are some other things to talk about. We're going to do that here. Um, so why are we using functions, say more than one function, in a program? Uh, what does it do for us, right? Because the structure of the program that we've been using in this course up until now is just to put all the code into main. We have one function, main, okay? And that's kind of the naive approach to structuring code, but it works well if your program is small. So the better practice for larger programs is to break up the code into the main function and an appropriate number of sub-functions. Now, when I say sub-functions, I mean that of the functions, some of the sub-functions will be called by main, and others of the subfunctions will be called by other subfunctions. So there's typically a hierarchy of functions that call each other. And exactly how to design that well is something that we cover when we get to Zelle chapter 9. So when we have more than one function, the main function becomes the orchestrating or coordinating function. And then the name main makes a lot more sense. So structuring your program like this makes the code easier to write, easier to read, easier to test, easier to debug, easier to modify. Okay, and I'm not saying it's immediately easier, right? I will admit that it's a bit of a challenge to come up with this idea that you're going to have a multifunction program. And so it might be stressful in the beginning, but once you get used to the idea, which we'll be doing here in chapter 6, and in a much larger way when we get to Zelle chapter 9, well, I think it truly will be easier to do all these things. So, there's a really popular term in programming, and it's a pretty new term, but it's actually been around maybe 20 years or something like that, and it's called refactoring. So, refactoring is changing a program that's already been written and tested to make it more readable, more testable, more maintainable without changing its function. Okay, and this is a big deal. I probably already talked about it a bit, and I'm going to be talking about it more throughout the course. And I have a link here to a site that's been organized by Martin Fowler, and we'll just go find it. Okay. It turns out that Martin Fowler is probably the most prolific writer on this topic of code refactoring. And he's probably not the only thinker in this area. And I think he does a good job of giving credit to other people who've contributed to this kind of refactoring concept. So in this, he has a refactoring book. It's called Refactoring. There are two editions of the book. Uh, the newest, the second edition, is the best and the most current, but the first one is pretty good even today. Um, and I just like to quote what he has to say here. So, refactoring is a disciplined technique for restructuring an existing body of code, altering its internal structure without changing its external behavior. Its heart is a series of small behavior preserving transformation. Each transformation, called a refactoring, does little, but a sequence of these transformations can produce a significant restructuring. Since each refactoring is small, it's less likely to go wrong. The system is kept fully working after each refactoring, reducing the chances that a system can get seriously broken during the restructuring. And he goes on in here, he has a lot of information in the website that's in the book, right? Uh, so there's a whole body of thinking well expressed by Martin Fowler about how to take a code that's not particularly well organized and how to organize it while keeping it working, right? And that's what refactoring is all about, okay? So, why are we talking about it here? Well, it turns out that each of the principles about how to change your code uh, to give it a more favorable structure, um, you can write it in an unfavorable way, right? Say, take the naive approach where all the code is in just one function, the main function, right? And then refactor it, okay, using the principles of refactoring, which we'll be learning about and practicing in the course. Or you could just think of those principles while you're writing the code the first time. Now, I have a word for this. I call it factoring. So, factoring would be organizing your code as you write it so that it's easy to read, easy to test, easy to debug. I didn't put that there, and easy to maintain. Okay. Now, most people don't use the term factoring. In fact, if you look up, if you were to do a web search on the term factoring, you would find out that it's a term from finance, which has to do with a certain kind of lending, right? Okay, so my use of the term factoring is probably not going to catch on, but it might catch on in your head, right? So what I mean by refactoring is applying the principles that we'll learn in the course about how to refactor and getting the benefits just when you're writing the code in the beginning. You know, don't write the wrong code and then restructure it. Structure it as you write it. Now, most people would just call this good program design. So this is essentially, well, this is one of the major topics when we get to Zelle chapter 9. So when we're doing the kind of refactoring that has to do with where the code is within the program, we do two things that you ought to have on your mind when you're writing the code to begin with. Okay, so one is called method extraction. So that's when you have a function that's too big, okay, and you want to take a piece of it and you want to pull it out and put it into its own function. Okay, and this is called method extraction because that's what the feature, there's an easy to use features of most IDEs, including PyCharm, that helps you to do this. And I demonstrate that in one or more of the tutorials. Okay, and um, that's what they call it in the IDEs, right? Okay, sometimes you can get too many things pulled out of the main body of code, and you have all these little functions hanging around. And you might say, I've overdone this method extraction. What I want to do is I want to get rid of the method, and I want to bring it up into the original function. And this is called method inlining. And they're the opposite of each other, right? Now, it's usually the case that we have too much code rather than too little code in a function. So when you're refactoring your code, how often, if you're going to move code from function to function, how often are you going to be kind of moving it down a level using method extraction? Well, I think you'd be doing that about 90% of the time, maybe 95. How often are you going to be bringing it back up to a higher level, method inlining? Well, 5% of the time, 10 at most, right? But you should know that these are common practices when you're getting the code in the right place. These are features of these IDEs, including PyCharm, and they're very easy to do. So my point here in talking about refactoring and coining the word factoring as another way to talk about program design is that these refactoring principles are as important when you're writing the original code as they are when you're improving it after the fact. Okay? Need to get to my next slide here. So, when we're trying to take our code and allocate it to various functions in the program, we want to follow some key design principles. And we're going to talk about these here, and we're going to talk about them again when we get to chapter 9, right? So for a long time now, like 45 or 50 years, knowledgeable people have said that the functions in well-designed programs should have two important properties: high cohesion and low coupling. Okay, so what are cohesion and coupling? Well, functions that have high cohesion are all about the same thing. Okay, they do one thing. Now, if you've got more than one line of code, obviously each line of code does a different thing. But I think what we're saying here is that you can look at the code that's in the function and you can see that it has an overall purpose, and you would be able to state that obviously. And you would be able to come up with a name for that function. Here's another thing. One sign of high cohesion is that the function is easy to name. You'd be able to come up with a name for it that wouldn't have the word end in it. So typically when we name Python functions, we use a verb noun phrase like print heading, read input, okay, write output, verb noun. Okay, one hint that maybe you've created a function that doesn't have high enough cohesion is that when you go to name it, you need a compound kind of name like print heading and one detail line and this and that. And then you're going, now, is there a common name for that, right? Like print a document? Well, maybe that's it. Maybe that's the whole document that you're printing. So maybe the name should be print a document. But uh, let's say that's not true. I mean, it's part of the document, but it's not the whole document. Well, then maybe you don't have things apportioned quite the right way. So there's a Wikipedia article that I point you to here on cohesion. Okay. And we're not going to read through it now, but that's a place where you could learn more about um, the value of having high cohesion uh, in your functions as you design them. Okay, now the other thing we said is we want them to have low coupling. Okay, so functions that have low coupling know as little as possible about the inner workings of other functions. Okay, so that means, for instance, a function that gets called shouldn't really care who's calling it, right? It has it's it is possibly expecting some input parameters. Okay, it has a mission that you can probably understand from the name of the function, and it's going to do some work. It's maybe going to have a return value, okay, and that's consistent with the mission, right? So it doesn't really care who calls it, okay? It doesn't really even want to know who calls it, okay? And then functions that have low coupling, in terms of the functions that they call, they only know about the interface of the called function. They know the name, they know the expected arguments, and they know any expected return values, right? So this is what we commonly call the interface, or the API, application programming interface, for the function that we're calling. So I gave you a link here to a Wikipedia article on coupling, okay? And again, we're not going to read through it, but it gives you an opportunity to begin to find your way to the literature on coupling. Okay, so as for the design principles for functions, we want them to have high cohesion. We want them to be all about the same thing. That's going to make them easy to name without using compound names. Okay, and then we want functions to know as little about each other as possible. The called function shouldn't really know anything about the functions that are calling it. It shouldn't care. Whoever wants to call it can call it. And then the calling function really only wants to know about the interface of the called function, the name of the function, the expected arguments, and the return values that it expects to get back. Okay? All right. Let's go to the next one. When you're factoring code into subfunctions, then you have to say to yourself, well, why am I doing it, right? And I've identified 4 common use cases here. Are they the only ones? No, they're not. But they're very popular, and as you do your programming and you're allocating your code to functions, you're going to find that very often when you do that, it's one or more, because they are overlapping, one or more of these 4 common use cases. Okay, so the first use case is one I call bags of code. Okay, so here's the situation that you're in. The the function that you're working in has too much code. It's too long. Okay. Now, how long should a function be? A good function size is about a page or less. Well, what's a page? Is it a printed page? Is it the size of your screen? Well, I'm not going to tell you exactly what the length is. I'm not going to say it's 18 lines or 36 lines or whatever. Uh, but you should be able to see it on a screen, maybe with a little scrolling around. But you ought to be able to get your head around what's going on in the function, and you ought to be able to see it pretty well visually. Okay? The bigger it gets, the more likely it is that it's too big. In this use case, code is going to be divided up into multiple functions that meet the size requirements, which is to say, when we're done, we've got more than one function, and none of our functions are too big. Okay, so I've got two of these demonstration programs that I want to show. O1 Bags of Code Original and O2 Bags of Code Refactored. And here's where the refactoring really starts to show through, right? When you restructure a code, right, you're refactoring it. Okay, so we're learning about proper, say, factoring or program design by looking at code that needs work. We're going to apply some of these refactoring principles, and then the result is going to be refactored code. So let's take a look. Okay, so we're going to take a look at O1 Bags of Code Original. Okay, and this is a program that prints the lyric to an Emily Dickinson poem. And this particular poem is Because I Could Not Stop for Death. And this is a pretty popular poem. I remember covering it in my English class in high school. And all the code is in one function in main, okay? And if we run it, it prints the poem Because I Could Not Stop for Death. Okay. Now, is this main too long? Okay. Some people would say not. Okay. So maybe you have to use a little bit of imagination to say, well, what if it were a longer poem? Or what if it were twice as long? At some point, you're going to get to the point where you go, you know, I've got to begin to break this up, okay? And if your sensibility is that you haven't gotten here quite yet, well, suspend your disbelief and play along as though we had gotten there, right? Okay, so how could we refactor this? Well, let's go to O2 Bags of Code Refactored, okay? And here's what we've done. We've taken the title line and each of the stanzas, which we're doing by number. So we have a function for write title line, one for write stanza 1, write stanza 2, write stanza 3, write stanza 4, write stanza 5. Okay. And now we call each of them in turn from main. Okay. And they've got pretty clear names. Okay. And they also have pretty high cohesion. For instance, we don't have a function called write title line and stanza 1, which would be doing two different things. Okay, it's hard to characterize that as one coherent thing. Okay, so even though write title line is a tiny little function, it's appropriate to have it here because it's got high cohesion. And if we included that code in stanza 1, it would lower the cohesion of stanza 1. Now, stanza 1 would be about two things, and not two things that have a good singular name. Okay? And then the other ones are all pretty straightforward. So if we run this, okay, we get the same poem, all right. We get the same output, all right, but we have a refactored program. And this is what refactoring is all about, okay? So, again, we're not doing all the refactorings that they talk about in the Fowler book or on the Fowler website. You can learn a lot about refactoring for a long time. I know there are more things for me to learn. But in terms of um, extracting methods from main, this is a great way to refactor it. And as I said earlier, uh, you can do it one of two ways, and whatever's easiest for you at your kind of level of development as a programmer. So if you do it the original way and then refactor it, well, if that works for you, great. Okay. Or if you can write it this refactored way from the beginning, well, it's not really refactoring, okay? And there is officially no term factoring. It's a term that I use. It's just good program design, right? So you can do good program design right out of the blocks, okay? Or if you miss it, you can find your way to it through refactoring. And either way, when you finish your program and it's well designed, you ought to be happy. Do things have to be perfect on the first iteration? They do not. Okay? You're going to find your style. All right. So that's that one. That's use case 1 that I call bags of code. Okay? Uh, we're just taking the code that we have and we're putting it into these bags and we're organizing it. All right. Let's go to use case 2. Use case 2 I call reusable parts. And I've got the term DRY after that. And people say that dry. And we'll get to dry in a minute. So here's the use case. We're looking at the code that we have at any given time, and we can see common code that appears 2 or more times. Okay, so it's a good practice to factor this repeating code into common functions that can be called from wherever the common code appears. Okay, this is going to save time in authoring. Okay, for instance, if we write it like this from the get-go, we're not going to have to rewrite that code every time we write it. The first time we write it, we're going to write it in a function, and then all the other times, we're simply going to call it. Okay, so it's going to be easier to write it, author it, easier to test it, because you really only have to test that code one time, easier to debug it, and easier to maintain or modify it over time. Now, when I learned about this years and years ago, we call this eliminating duplicate code. But the more current writers have a phrase, don't repeat yourself. It means the same thing. And they have an acronym for it, DRY, dry. And I think that dry is an easier way to remind yourself of these. So I think that this is a pretty good teaching tool. So what I have here is two more programs from the demonstration project. We have O3 reusable parts original and then O4 reusable parts refactored. Okay, so let's go and take a look at reusable parts original. Okay, now when we're showing the use cases for functions, it's not uncommon for us to have you print out uh, uh, a, a poem or the lyrics to a song. Why is that? Because they often have a refrain that repeats. Okay, so here, this is a program that prints out the lyrics to the Bob Dylan song "Blowin' in the Wind," and of course, it has a refrain. The answer, my friend, is blowing in the wind. The answer is blowing in the wind. Okay, and there may be some other opportunities here. So we look at the code, and again, you tell me if this is too long. Maybe it's not too long. Okay, but we do have repeating text. Okay, and having two parts of the program that create the same text or that do the same function um, is repeating yourself, okay? And it's leaving some opportunity on the table to uh, uh, reduce duplicate code. So again, if we run this, we get the lyrics to "Blowing in the Wind." Okay? Apologies to Bob Dylan. Okay, so let's look at 4 reusable parts refactored. And by reusable parts, I mean, the use of reusable parts has been very important in modern engineering, and then of course onto manufacturing, and it's done a lot for commerce, and it does a lot for programs. And so what we're going to hear is how do I break this up? Well, I've got something called write title and credits. Okay, you tell me if you think that write title and credits has high cohesion. I put this in here so we could talk about it. This "and" word is very suspicious. If you have a if you have the name of a function that includes the word "and," okay, I'm going to say that the presumption is going to be that this isn't a cohesive function. Okay, so could I have called this "write front matter"? Or perhaps if I knew more about songs or poetry or publishing, I could come up with a single term for this. Okay, but right now with this "and," it's very suspicious. Okay, so I've got this. We're not sure that was a good idea. And then we've got verse 1, verse 2, verse 3. Okay, we got 3 verses, and there's a refrain. So there's a refrain at the end of verse 1. This is, and we made that into write refrain, and that has that repeating lyric, and that's called from verse 1 and verse 2 and verse 3. So this refactoring is an improvement, okay? You might argue that I'm not done yet. I need to turn this into 2 functions, okay? I would say that might be a valid argument. Either that, or I need to come up with a better name for this that is true in terms of the terms of art that people use who publish song lyrics, right? And I don't know. I can't tell. Uh, Maybe they call the whole thing the credits. I don't know. We'll find out. Okay, and then when I run this, I get the exact same output. And again, refactorings are not changes in the function of a program, okay? So you have a program when you start that works, okay, that gives you good results. But you don't think that it's structured in a way that gives you, that makes it easy to write, easy to read, easy to test, easy to modify. Okay, so we change it, but a big thing to remember is we don't change the output. The output should be character for character, action for action. It should be the same thing. Now, there are times when we have a program that's got two problems. Problem one is that it doesn't meet all the requirements that we want, and the other one is it's not well structured. And what the refactoring folks would say would be, well, then fix it. If you can possibly fix it the way it currently is, well, fix it first and then get into restructuring it with the refactoring principles. Um, or if it's so confused you can't fix it, well, then the refactoring will, the test of it is that in the beginning it's going to give you the exact same results, and then at some point in the evolution of the program, you can intervene and change the functionality, right? But you're not supposed to be doing both at the same time. Refactoring should preserve the function of whatever you have. Okay? So that's reusable parts. Well, wasn't supposed to do that. Sorry about that. So the third one, which also is part of the dry principle, I call parameterized tools. Okay, and here's how we know that this use case uh, is uh, is here. Okay, so there are multiple pieces of code in the original code that are not exactly alike. Okay, so it isn't like that we can just go and do reusable parts because they're not exactly the same. Okay, but they're sufficiently similar to be addressed by a function that takes parameters. Okay, so uh, we can write a common function. Okay, that function can be called with parameters, and that will customize each call, and then it's basically the dry principle after that. So again, it's going to save authoring time and testing time and debugging time and maintenance time. And it's part of the dry principle. So I've got two pieces of code to show. O5 parameterized tools original and O6 parameterized tools refactored. So let's take a look at that O5 one. Okay. So uh, here we're doing some similar stuff. Okay, I must admit that the the ability to see these opportunities, it's something that grows on you as a programmer over time. Okay, so here's what we're doing. We've got some text and we're analyzing it. Okay, so the target statement that we've got is the quick brown fox jumped over the lazy dog. And this is something that they used years ago in in typing school, which they would now call keyboarding school, yes. Uh, and so we have the target, we have a shifted target, which shifts it to lower. We only got one upper, but that's it. Uh, and then we have the vowels A, E, I, O, and U. We have the consonants. They're listed. We have spaces. Here's a space. We have the punctuation marks that we care about. There are more punctuation marks in the Unicode character scheme, but those are the ones that we're interested in here. Okay, so the code as we have it, it prints out the target string, okay, and then it analyzes it for how many vowels are in it. Okay, so we say for cat, we initialize the vowel count to 0, and we say for character and vowels, vowel count plus equal shifted target count character. So we're counting each of the characters as we go through. So when we're done, we should have the full count of all the vowels, and then we print that with an F string. So we do that for vowels, then we do this for consonants, then we do this for spaces, then we do this for punctuation. Now, are we doing the exact same thing every time? No, we're not, because we're checking for a different list of characters each time. But there is a pattern here. And this is where you're going to say, I think I need to build a common function that takes parameters, and that common function is a parameterized tool. That's why I call this parameterized tools. Okay. All right, so how could we, and let me run this. So I run this, and here's what we find. The target string is, we see it, it contains 12 vowels, 24 consonants, 8 spaces, and 1 punctuation marks. Now, maybe someday we could say 1 punctuation mark. Okay, there's an opportunity there that we can maybe capitalize on when we get done with chapter 7. Okay? All right, so we have a lot of code here, and yet we're doing 1, 2, 3, 4 of very similar things. It looks like if we build the right parameterized tool, we can squeeze that down to having one common function that we call with the right parameters. Okay, well, let's see that actualize. So the beginning of the program is the same. Okay? All right, now I wrote this in a pretty summarized way. What I did is I created a function called count qualifying characters. Okay, and it's expecting two parameters: string to be analyzed and qualifying characters. That's a string as well. Okay, and what does it do? Well, it sets the overall count to 0. It shifts it to lower because that's important for some of them. And then we say for character and qualifying characters, and then we do the same thing. We do a count, and we keep accumulating it. And then we keep accumulating into overall count, and then we return overall count. Okay, so when we want to do this for vowels, well, we pass in vowels. When we want to do it for consonants, we pass in consonants. Spaces, we do spaces. Punctuation marks, we pass in that. Okay, so we do the same thing each time. We call count qualifying characters, okay, and we pass it the target. That's the same every time, so that helps. And then what we want, and then we put this together with these F strings such that it really made the code easy to read. And if we run this, we're going to see the same output, right? So I'll admit this is a little more challenging to look at the original code before we refactored it to use a parameterized tool. Okay, but what happens is that over time you start to see these patterns and you say to yourself, you know, there's a pattern here. I bet, this isn't exactly common code that we can factor out easily using reusable parts as the use case, but with just a little more creativity and some parameterization of the function, we can replace all these things with a parameterized, with calls to a parameterized tool. Okay? So that's parameterized tools. Okay. So that's the third of the four use cases that I wanted to show you. And now let's go on and look at the fourth. The fourth one is not so very different from the last two. It's called hiding places for assumptions. So here's what's going on in the code that helps us to recognize it's time to do this refactoring. There are multiple pieces of code that do similar work, but replacing them with function calls is not going to save very many lines of code. So most of the last two that we did, reusable parts and parameterized tools, you can really see that we're saving lines of code, right? And so you can really see the rationale, okay? But there are some times where you still want to put something into a function, even if you're not going to save any lines of code. And as a beginner, sometimes it's hard to get your head around this. So replacing these bits of code with calls to a function may not save any lines of code yet. We do replace these code pieces with calls to a common function. Our rationale is to isolate some assumption regarding how we solve the problem and just locate it in one function only. This is going to save maintenance time should that assumption change in the future. So what's interesting is as you get more experience about how requirements for programs change over time and you're coding your way through them, you begin to get sort of an itchy sense. Oh, you know what? The client's going to come back and ask to change that. I had better isolate that in a function so that when they change it, I've only got one bit of code to change. Okay? So the example of this, we have a 07 hiding places original, and then we have 08 hiding places refactored. Okay? So let's go take a look at them. So in hiding places original, we're not doing anything very fancy at all. We have a block of text that we're trying to print, and it includes the name, the street address, and 3 phone numbers for Jane Q, the scholar, and she's one of my classic examples that I repeat a lot. Okay, so in this original version, okay, we print the name assembled. we print the two parts of the street address. We print the city, state, and the zip code, and then we print a sort of a header string for the home, the work, and the mobile phone number, and then we format them. Okay, and it looks like the way that we're formatting them is we're doing 3 digits, a hyphen, 3 digits, a hyphen, four digits. And this is a pretty common way that we format phone numbers here in the US. So let's print these. Okay. And you can see our three phone numbers have the hyphens. Okay. Well, there's not a lot of code here. Why would we want to do anything else? Well, there's a possibility for us to take the assumption about how we format a phone number and hide that assumption in a function. So this is where we get to 08 hiding places refactored. So so what we've done here is we've created a function, format phone string, okay, and we pass in the phone number. And this, in a way, is a parameterized tool. So you could say, well, Kevin, this is just parameterized a tool. But I'm just going to point out, it doesn't save you any lines of code. Okay, so you might talk yourself out of this parameterized tool. Okay, so what we do is that we know now, because we've got one line of code that formats all phone numbers, and again, it puts in the hyphen, it puts in the two hyphens. Well, we're going to get the same results, right? So let's look at this. So again, it's a refactoring. Refactorings do not change the functionality. They just change the structuring of the code to make them easier to write, easier to read, easier to test, easier to modify. Okay. Now, this is easier to modify. Now, what if the client came back and said, oh, Kevin, I really like what you've done here, but we've talked to our graphic designer and we want to use the more trendy way to format a phone number. Instead of the hyphens, we want to use the period, the dot. And I go, okay, that's fine. I just come right in here and I put a period here and I put a period here. So I just change a single line of code and I rerun it, and all three of the phone numbers are formatted the right way. Now, if you were only thinking about lines of code or, code saved as your rationale for, extracting a function, you probably wouldn't do this, okay? But once you get a sense for what clients are going to come back for and ask for it to be different, or what technology changes are going to happen, so that you're going to have to change the way you implement something or other, it gives you the opportunity to extract functions that you wouldn't otherwise extract based simply upon lines of code saved. And now I put this back in its original state, and we're back to the hyphens. Okay? So that is hiding places. And this concept, this has been around for a long time. Glenn Myers, I think, used to write about this 50 years ago. He was a very influential computer scientist and writer, and he called this assumption hiding, which is why I call this hiding places for assumptions. And this has been a good practice for a long time. Not something that gets included in uh, courses for beginners all that often. Okay, we've got a couple of more things to talk about before we wrap up. So, it's important for you to have a good idea about, kind of the plumbing of Python functions. Okay, what you can pass into them, what they return, all those kinds of things, right? And I think that the Zelle books does a pretty good job of talking about a lot of the issues, but um, I want to talk about them in my own way. Okay. So all Python functions return a single value. Okay. It might not seem like it, but it's true. Okay. So if the function that you call has no explicit return statement in it, then the value none is going to be returned. That's why this Zelle tells you if you're testing your program and all of a sudden in the output you see the value none, you might want to think that maybe you forgot to return a value in one of your functions that was supposed to return a value. Because if there's no return statement, the value of none is what we return. If the return statement returns exactly one value, then that value is the value that we return. Okay? And we're used to that. Now, here's one that I think he talks about it in the Zelle book, but I really want to emphasize it. If the return statement appears to return more than one value, then a tuple is created and the tuple is returned. So again, in some sense, we're returning multiple values, okay? But mechanically, we are returning one thing, a tuple. Now, the fact that you can return more than one value and the mechanics are that it's a tuple, this is not an excuse to design functions that lack cohesion, okay? So even though you can return more than one value, we still want to design and implement functions that are highly cohesive, that are all about one thing. So if we're returning more than one value in the tuple, then the items that compose the tuple should be about the same thing. And we'll show you examples of those, right? So I've got two more demonstration programs I want to show you. O9 use function returns more than one value. So we're going to call a built-in function, and it's going to return more than one value. And then 10, we're going to create a function that returns more than one value. So one is use and the other one is create and use. All right, so let's look at 9 first. 9. Okay, so here's what we're going to do. We're going to create this little thing called integer division calculator. And you'll remember that when we were working in chapter 3, we did some division using Python integer division. And so we would get the, we would take the dividend, that's the big number that you're trying to divide. We would divide it by the divisor, that's the smaller one that you're dividing by. And if we use the slash slash, we would get the quotient, okay? And then if we used mod or the percent, we would get the remainder. Well, it turns out there's a built-in function in Python that's pretty popular, and you can use it for integer division, and it will give you both. It'll give you the quotient and the remainder, and it's called divmod. So you call divmod, and you pass it the dividend and the divisor, both ints, okay? And then you get back quotient and remainder. Now, they're in a tuple until you unpack them, okay? But it's pretty typical to just unpack them right off the bat, and then you can use them to display to the user. So then we display the quotient is quotient and the remainder is remainder. So let's run this. So welcome to Easy Integer Division Calculator. Please enter an integer value for the dividend. Let's say 11. That's pretty big. And please enter an integer value for the divisor. Let's say 5. And then it says the quotient in 2 is 2 and the remainder is 1. Okay, so this is one of the few popular functions that returns more than one value. Mechanically, it comes back as a tuple, okay? And they're really about the same thing, okay? I know that Zelle has an example in the textbook about sum diff, okay? And I argue that those are not about the same thing. But here, the quotient and the remainder, they're all about dividing, okay? They're the two parts of the answer when we do integer division. And this was a brilliant design of the function divmod. Okay, so this is how you would use it, and it's already built in. How could you create a function that returns more than one value? So let's look at a 10, create function that returns more than one value. So what we're going to do here is we're going to take a peek ahead to some work that we do when we get to Zelle chapter 9 when we're working on game simulations, okay? And one of the things that we do, I think it's in a tutorial, is that we have a dice game, okay? And so what we're going to do is we're going to roll 2 dice, and then we're just going to say what we rolled, okay? So we're going to do is we're going to create a function called roll 2 dice, okay? And it's going to pass back a roll result, okay? Well, we're getting 2 things back. It's probably a tuple. So we're going to print the roll result, okay? And we're also going to print the type, okay? Now, we could have immediately unpacked the 2 values that we got back. Instead, I wanted to show you the tuple, okay? And now we're unpacking it into left and right. Now, when you roll 2 dice, there's not one that you can tell is the left one or one that's the right one. When you roll them, maybe one's on top of the other or one's in your shoe or whatever. But I'm just pretending that we can characterize one as being on the left and one as being on the right. So that's why I use that. And then I can print with an F string. The left die value is left and the right die value is right. Okay, so let's test that first before we go look at how we create it. Okay, so we printed tuple 3, 5. We rolled a 3 and a 5. The type of it's a tuple, and then the left die value is 3 and the right die value is 5. And when they come back on the tuple, there is one on the left and there is one on the right. And that's one of the reasons I like to do that. And if we run that again, we'll get other values. 6, 3, 6, 3, 2, 3, 3, 6, 5, 1, 5, 3, 2, 1, right? Now, how do we do this? Well, in order to generate a random a digit between 1 and 6, we're going to use the random package from Python. We're going to import the function randint. Randint generates a random integer, and we tell it what the boundaries are. Okay, so what I've done is I've created a function down here, and it returns the roll of one die. I call it roll one die, and I pass it randint 1 6, and it turns out that the second parameter for randint includes the highest value. I know a lot of the functions in Python, you give it one pass what you want. So, for instance, you might think to get a number between 1 and 6, you'd have to put 1 comma 7, but you don't. You put 1 comma 6, right? Now, a lot of people would think, well, why do I need to create something that rolls one die? That's not going to save me a lot of lines of code because it gets called by the function roll 2 dice. And what do? I call roll one die and I call roll one die again, and I assign them to left die and right die, and then I return them. Here's how you return two values. Okay. And somewhere there is some writer in Python who emphasizes the fact that when you create a tuple, what really creates the tuple is the use of a comma between the two data names. So he would say the reason we get a tuple here is that we use a comma. Okay. Now, when we're returning more than one value, we do not create a tuple explicitly. We don't do this. Okay. Because it'll get underlined and complained about. I think it says we have extra parentheses. Is that what this says? Remove redundant parentheses. It's better to think of this simply being the two values that we're returning, and the Python infrastructure is creating the tuple. But why did I create roll one die? Well, this hides the assumption about how we roll a die. And if it turns out that we're going to use another package and another function to generate a random value, well, we've only got to change it here and here, even if we were rolling dice all over the program. Okay, so these are the mechanics of returning more than one value. Okay, and this is done here. Return first name, comma, next name, comma, next name, comma, next name. These both have to do with the same thing. This is a cohesive function. Okay, why? Because it's easy to come up with a cohesive name for it. Okay, we're rolling the dice. We're rolling two dice. And then we get the results back. We can access the tuple as a tuple. We can just hang on to the tuple. And we can unpack it if we wanted to unpack it immediately, like we did back here in this thing where we called divmod. We didn't hang on to the tuple, we just unpacked it right away. We can do it either way. So those are the mechanics of returning more than one value. Remember though, We don't want to create functions that do 2 and 3 and 4 things. You know, could you create a function that does 2 and 3 and 4 unrelated things? And could you have it return 2 and 3 and 4 values? Yeah, you could. It'd be horrible design. You don't want to do it. Why? Because it's not cohesive. So, one more thing that I want to tell you about, and I'll let you go. Positional and keyword parameters. So the parameters that we've been using throughout this chapter 6 stuff are all positional parameters. Okay, so with positional parameters, the arguments in the calling code, it's sort of interesting that the names we use in the calling code in almost all languages, we refer to those as arguments, and then the names that we use in the called code on the function header, the names that appear in the parens. In Python, they're called formal parameters. Okay. Sometimes in Python, they call the names that we use in the calling code, they'll call them actual parameters. And I've tried to do that. One of the textbooks that we use, if not both, are calling them actual parameters. But it's probably better to call the names on the list in the calling code arguments and the names on the list in the called code parameters. Okay. So with positional parameters, the arguments in the calling code are matched up with the formal parameters in the call code by position, by order. Okay. But Python also has keyword parameters. Now, I don't know that whether we've seen them yet, but we're going to see them now. And these are matched by name. Now, the syntax is such that you have to code all the positional parameters before you code the keyword parameters. One interesting feature of keyword parameters is that they provide default values, and this is one of the reasons why people like to use them. So let's see how they work. We've got two programs. We've got 12. One is a use and one is a create. So I'm going to show you how to use a function that takes a keyword parameter. It's a built-in function that we already use. It's the print function. And then we're going to learn how to create one of our own. Okay? So let's go to 12 use. Okay. So we're going to demonstrate using a function that takes a keyword parameter. And some people in class have already used it because I've seen some code when we were reviewing their solutions, right? It turns out that the print function, it takes normal positional parameters, but it has a keyword parameter called end. Okay, and the way you code a value for a keyword parameter is again, after all the positionals, you have a comma, and then you have the name of the keyword parameter, an equal sign right next to the name, all jammed up, and then the value right next to the equal, all jammed up. Whereas with assignment statements, like this one up here, we tend to spread them out with an intervening space. The official style for keyword parameters is they're all jammed up here with no intervening space. So it turns out that the print function has a keyword parameter end. Okay, so let's toggle this into a comment and let's look. We have a list of values from 0 to 20 by 2s in a list. okay, and then we print some title stuff, and then we print for value, and values print value. Okay, so let's see what that looks like. Did not run that, so I don't know what I was doing there. So we did not want to do that. Okay, so let's try that again. We're going to run, and here's what we got. We got each of them on their own line, okay? And so even though we didn't code anything that had the sequence for new line in it, we got a new line at the end of every line that we printed, okay? And we're used to that, so we're not surprised, okay? Well, oh, I got rid of all my code. I shouldn't have done that. Uh, there'll be a slight pause while I fix that. Okay, I fixed that. Okay, so this is the first group of code. It behaves exactly as we thought. Okay, so let's bring in the next bunch of code. Now this is the same except that I've coded this end keyword parameter. Okay, the end keyword parameter gives the text that goes on the end of the line. Okay, and the reason why we always get a line feed is that the default for end is a new line. Okay, so how do we know that that's true? Well, here's what I'm going to do. I'm going to get rid of. I'm going to toggle the original code into a comment. This code's the same except for it explicitly has the new line, and we're going to run it, and we're going to get the same output. So the default value for the end keyword parameter is always new line. Okay, well, what if we gave another value for end? Okay, what, for instance, what if we wanted to kind of use it as kind of a separator, okay, between the values? Instead of putting out a new line, let's put out a comma space. Let's see if that would look good, okay? So we run that, and look, we get 0 to 20, and we have comma space, comma space, comma space. And we go, oh, that's not really coming out as a separator. We didn't really want one at the end. So that is an interesting idea, but it doesn't really do what we wanted to do. There is a way to create a way to separate things in a list, and we'll eventually be using it. But now, how could we use the end keyword parameter to do something that would look okay? Well, it turns out that we can just say end equals space, which we did here. And if we run that, that's going to look pretty good. They're separated from each other. There is a space on the end, but we can't see it. So it does put a space at the end. Okay. So why do we use keyword parameters? We usually use keyword parameters when we want to have a default value for something, okay? And which is why you can code a print and not provide a value for the keyword parameter end. It defaults to the new line character. All right. So let's take one more program, let's look at one more thing, and say how we could create our own function to do this. And this is kind of an arbitrary function, but here's what we want to do. We want to create a function. We created a function just called multiply it, okay? And it takes a value in, okay? and then it multiplies it by a factor. Okay, so value in is a positional parameter. A factor is a keyword parameter. We know because it comes at the end of the list and it has a default value. Okay, so the default value is 2, and then we return the value in times the factor. Okay, so what we're going to do is we're going to show what happens when we call it here. We set value equal 3, and then we say higher value equals multiply it value. We don't provide a value for factor, so we're going to get the default 2. So we're going to expect to see the answer 6. Okay, and let's toggle this one into a comment. Okay, and let's run this. And what do we get for an answer? We multiplied a value of 3 by the default factor to get 6. Okay, and then let's bring this other code in. Okay, and so we have the factor is equal to 3. So now we say even higher value, we call multiply it, we pass value, that's the positional parameter, and then we code factor equal the factor. That makes it equal to 3. So then we print then, we multiplied a value of value by the factor to get even higher value. So we're going to run this, and we're going to see, then we multiplied a value of 3 by 3 to get 9. Okay, so we won't be using this a lot, but there are situations in the code that we are going to do where we're going to be calling functions from the Python standard library that take keyword parameters like print does, and eventually the very last thing that I'm going to do is I'm going to be doing a demo in the class of the pandas library, and pandas uses keyword parameters a lot. And so even though I'm not going to emphasize you designing the use of keyword parameters into your code, I mean, you can if you want, I want you to see keyword parameters as just a basic Python function. And so when we see them in the code that we're going to use, they're not going to have any kind of magical quality. They're just going to be a basic Python feature that we don't use every day, at least in the kind of coding that we're going to be doing in the course. And that is the end of this Beyond the Textbook lecture. I showed you links to a couple of places, and I've included the links again here with proper attribution, and so you can use those in order to find your way to the resources. So with that, I'm going to say bye until next time. Bye-bye.